All right, ladies and gentlemen, this is going to be reaction rates in our next video. So let's get started. So reaction rates are kind of like demolition derbies. And in a demolition derby, you have two cars that smash into each other. And what ends up happening is the one that is left at the end is the winner. So you put all these cars in a field and they go through and they smash into each other, and the one that's left running at the end wins. Well, reaction rates are kind of like this, and we call this chemical kinetics. And chemical kinetics is simply how molecules smash into each other. And we can see chemical kinetics in action as these molecules go through and move around in this container. Now, dependent upon how the molecules interact, they can bounce off of each other, or if they're lined up perfectly right, what we get is a chemical reaction. And what ends up happening is then all of the molecules that we had in this particular mix get separated and broken up into products. So if we look at this reaction here, we can see that the molecules are lined up perfectly. Then they go through a collision. Now, we call the reaction rate simply how fast the reaction occurs. So we can see this chemical reaction occur here. We have a reactants that we start off with. Now these molecules are lined up perfectly that we're going to get a collision that involves breaking the molecules down into atoms, and then we get our products here. So this is a chemical reaction, and chemical kinetics is simply how fast the molecules smash into each other, and reaction rates is how fast it occurs. So when I say what are reaction rates, well, I'm really saying how fast the reaction is going to go through and occur. Now, there's going to be a few things that go through and affect it. The volume, the quantity of the particles, the temperature, the surface area, and then also if there's a catalyst present. All 5 of these things are going to affect the rate of reaction in a chemical reaction. So let's talk about collision theory. Collision theory states that in one particular case, when a molecule collides, then a reaction will occur. And in most cases, the molecules have to be lined up in a certain way where they go through and collide and then turn into their products. So we can see these molecules moving around in this container. And remember, all of them have energy. But if we look at this again, we can see that if we increase the speed, then what we get is a chemical reaction. Well, why do we get a chemical reaction when we increase the speed of each of these molecules? This is something that we're going to talk about now, and it all comes down to probability. So when we increase the temperature of a particular medium with chemicals in it, we're increasing the quantity of energy that it contains. If we decrease the temperature, then we're decreasing the quantity of energy. Now, if we compare the speeds in the molecules here, the temperature is lower, and we can tell because the molecules are moving slower. If we compare the speed here, though, we can see that the temperature is faster. And when that occurs, the molecules move faster because they have more energy, and we have a higher probability of a chemical reaction occurring. So let's look at temperature. If we increase the temperature, what it does is it increases the quantity of energy that is in the medium, and the particles move more quickly. When the particles move more quickly, particles collide with more energy, but they also have a higher probability of going through and colliding with each other because they're in more places over a shorter period of time. When we increase the temperature of reaction, we get the fastest reaction here. And that's because what we've done is we've increased the speed at which they're moving. So one, they're colliding with more energy, but they also have a higher probability of colliding with each other. So if we decrease the temperature, well, it's going to have the opposite effect. So if we decrease, the particles are moving more slowly, and the particles are going to collide with less energy. Because of that, we're going to get a slower reaction, and we can kind of see that modeled here. Now, the other thing that's going to affect the rate of reaction, or how fast or slow the reaction occurs, is the volume, or the amount of space that the molecules have. So these molecules have a lot of space, so they have less probability to go through and collide with each other. But if we shrink down the volume of space that they have, now when they're moving around, they have a higher probability of hitting each other because we've shrunk down the space. So if we think about this, then if we go through and we increase the volume, well, there's more space for the molecules to move around, So there's less probability that the molecules are going to go through and collide. So therefore, the reaction is going to occur slower. And if we go through and decrease the space or the volume that the molecules have, well, then we're going to have a higher, or it's going to be more likely that the molecules will collide. So therefore, the reaction is going to occur faster. Now, the other thing we have to think about is concentration. So right now I have 3 molecules in this container. Now, if I want the reaction to occur faster, well, I can add more stuff. If I add more things, if I add more molecules where there's a higher probability of them going through and reacting with each other. So if we think about concentration here, if we increase the quantity of molecules or the concentration of the molecules, well, then we're going to have a higher probability of the molecules colliding. And if we go through and increase the concentration, well, our reaction is going to occur faster. We're also going to get more of a product because there is more stuff. Now, if we think about concentration here, well, if we decrease the concentration, well, then we're going to have less probability that the molecules will collide. And because of that, our reaction is going to occur slower. Okay, the next thing we have to think about here is surface area. Now let's think about this cube here being a salt cube. So we have our chlorine here and we have our sodium molecules, and we're thinking about it in a 3-dimensional cube. Now let's say we were to go through and dip this into a glass of water. I'll draw the water here like this, and we'll go through and draw the top of our water here. It's not perfect, but it works. Now if we think about dipping this cube in this jar, well, the only thing that's really going to come in contact with the water molecules, if we were thinking about our water molecules being here, well, the only thing that's really coming in contact with that is just the surface of the cube here, each of the 6 surfaces of the cube. The molecules in the center are not really coming in contact with the water because the water has to eat away at all of these surfaces first. Because of that, the reaction is going to occur slower because it has to go through and eat away at that cube. Now let's say I had that same jar and then I broke and crushed up that cube of salt and then I threw it in the jar of water. Well, now because of that, because it's all crushed up, each of the individual molecules can go and come in contact with our water molecules here. Because of that, each one of the molecules can go through and react with our water molecules. When that happens, the reaction rate's going to occur faster because now again we have a higher probability of molecules going through and hitting each other. So these molecules can go through, the chlorine here and the sodium can interact with the water now because each one of the molecules is broken down here, and now our water molecules can go through and bind and chemically react with the sodium. Again, it's a game of probabilities here. And these water molecules, because now that all of our molecules are exposed, now they have a higher probability of reacting with the chlorine and the sodium molecules here. So if we think about surface area here, well, if we increase the surface area, then what we're going to get is a faster reaction because there's a higher probability of the molecules interacting because it's all crushed up. So reaction's going to occur faster because now each of the individual molecules can react with our water. Now, if we just have the cube of salt here, well, now we've gone through and decreased the surface area. When we've decreased the surface area, we're going to get less probability of molecules that will interact, and because of that, the reaction's going to occur slower. So when we crush stuff up, we've increased the surface area, so therefore the reaction occurs faster. And if we go through and keep it in a cube form or some sort of dense compacted form, well, the reaction is going to occur slower because there isn't as much surface area. And our 5th and final thing that's going to affect our chemical reaction is going to be our catalyst here. Now, a catalyst goes through and lowers the activation energy. And there's a certain amount of energy that's required to go through and start a reaction. And reactions, again, are going to require energy. So on the y-axis, we have energy here. And then on the x-axis, this is going to be time. Now, when I'm talking about activation energy here, I'm talking about the amount or the quantity of energy. Sorry, quantity of energy to start a reaction. We'll put reaction abbreviated here. So quantity of energy required to start a reaction. Now, a catalyst here, a catalyst is simply a chemical that goes through and lowers that. So if we look at this from here, from this point here to this point here, well, this was the amount of energy it originally required to start our reaction. But we can see when we add our catalyst into the chemical mix, it only requires this much energy. So now what we've done is we've saved all of this energy here that it used to require to start the reaction, and now we only have to use up this much energy to get our chemical reaction to occur. So we can see as we go up here, this is our chemical reaction occurring, and this is the energy to get it started. And then we can see as we go down the slope here, this is the formation of our products here. So we can see energy without the catalyst, that's from here to here, and then energy with the catalyst, which is just a chemical or simply another chemical here. This has gone through and decreased the quantity of energy. When we decrease the energy required, in many cases, it's going to decrease the quantity of time needed to go through and have this chemical reaction occur. And it can affect the reaction rate. Now, in this case, if we were reading this graph, it required less energy, and it looks like our products are going to be formed at similar times here. But the thing we want to keep in mind is sometimes the catalysts are going to affect how fast the reaction goes through and occurs. And in this case, a catalyst is going to go through and affect the amount of energy that's required to go through and have that chemical reaction occur. So, did you guys learn? Well, did you learn a couple of things? Did you learn what a reaction rate is? So it's simply how fast or slow a chemical reaction occurs. Did you guys learn the 5 things that affect reaction rates? And did you guys learn how molecules really interact at the molecular level and what it really means to have a chemical reaction? This is going to be the end of the video. I will see you guys in class tomorrow.